Hello friends, I welcome you to yet another episode of Learning Physics with IBM. Today I'm recording a special video for my friend in Kenya who was facing challenges with manipulating base units. He requested me to use past paper questions to make him confident with handling base units or deriving base units. And I know as an AS physics student, you will also benefit from this video and you'll become confident with the first unit or the first chapter of AS physics. So in AS physics, you talked about physical quantities and base units, that as the first unit. You mentioned, or your teacher mentioned, that there are those quantities which can be measured with a certain instrument and therefore they can be quantified given a magnitude with a unit. Those quantities, you call them physical quantities. They were classified into two. There are those that we call the fundamental or base quantities, from which all other quantities in physics are going to be obtained. Then there are those that you call the derived quantities. So the units of the fundamental quantities or the basic quantities, you call them base units. And those units for derived quantities, you call them derived units. So actually, the derived units could always be expressed as base units because they would be expressed as units of the base quantities. So today I want to help my friend become confident with handling base units, and at this point I want to start. But don't forget, uh, comment, like, and share this video with the friends that are learning physics. Okay, so let us start with question number one. Let's start with question number one. Remember, all these questions are picked from past paper questions. And question number one is, of course, it's about electric fields. I don't expect such a question to appear again in AS because for examination starting 2022, I think electric field strength or electric fields were removed completely from AS. You'll find electric fields in details in A level. You may not find it in AS again. But of course, I needed this question to help us just understand the basics of how to obtain base units of a given quantity. So we have been given that the electric field strength is labeled E, and at a distance x from an isolated charge Q is given by this expression here. So we are going to use that expression. B is a constant, but they have not told us whether it has units or not, so we don't need to bother about that. So the question wants us to use the definition of electric field strength to show that E has these base units. So let us begin. So electric field strength E is defined as the force acting on a unit positive charge. The force acting on a unit positive charge is what we call the electric field strength. So to begin with, charge is defined as I times T, which is current times time. Current is a base quantity, its unit is a base unit. Time is a base quantity, its unit is a base unit. We know that current is measured in amperes, so the base unit of current is amperes. Time is measured in seconds, the base unit of time is seconds. So combining those quantities and their units, we have that the base units of charge are going to be ampere seconds. On the other hand, force is expressed as mass times acceleration. And we know that mass is a base quantity, is one of the 7 base quantities. So mass is measured in kilograms. Therefore, its unit is a base unit. We can't express it any further. Then on the other hand, we have acceleration, which is defined as the rate of change of velocity or change in velocity with the time. We already know the base unit of time. But then velocity is also defined as the rate of change of displacement, that is changing displacement with time. Because displacement is a length, its unit is meters, time unit is seconds. So we now conclude by saying that the base unit of the speed or velocity is going to be equal to meters per second, that is meters divided by seconds. When I take back this to this expression here, it means that the base units of acceleration are going to be those of change in velocity divided by those of time, which simplifies to meters per second squared. Therefore, I was actually finding the base units of acceleration. So the base units of force, which is mass times acceleration, will therefore be kilograms times meters per second squared. So now I'm good enough to go. I now go and substitute in the expression for electric field strength. Force is kilogram meters per second squared divided by charge, which is actually ampere seconds. And when you simplify this becomes kilograms meters. When ampere goes up, it becomes per ampere. Then when S goes up, mathematics window, here I have a mathematics window for you, especially those doing PCB. So I have S power negative 2 divided by S. This is S power negative 2 minus 1. We subtract the powers, so it becomes S power negative 3. So that means this will be S power negative 3. So we have been able to show that the base units of electric field strength are kilogram meters per ampere per second cubed. That is from the definition. Okay, let's proceed to the next part. So this is a continuation of question number 1. And it is still telling us that use the units for E given in B Roman 1 to determine the SI base units of B. So we have found the base units of E. We have seen that the base units of E sorry about that. So we have seen that the base units of E are actually kilogram meters per ampere per second cubed as given in part 1. And they have also given us that E is equal to Q divided by x squared times B. Remember, x was defined as distance, Q was defined as charge, E was electric field strength, and B is a constant. So we want the base units of B. So what do? We make B the subject. So B will be equal to, making B the subject, that will be Q divided by EX squared. So that is B. But remember the base units of Q was charge, that was ampere seconds. We already have the base units of E. X squared, X is a distance, so the base units of X squared will be meters squared. So all that remains is substituting this expression. So the base units of B will be equal to the base units of Q, which are ampere seconds, divided by the base units of E, which is kilogram meters per ampere per second cubed, multiplied by meters squared. So that those will be the base units of B. And when we simplify this, of course, when kilogram goes up, it becomes per kilogram. And when per ampere goes up, it combines with ampere, it becomes ampere squared. When meters combines with the meter squared, it becomes, and it goes up, it becomes per meter cubed. When S is divided by S power negative 3, we subtract the powers, it becomes S power 4. So these will be the base units of the constant B as required by that question. Okay, so I hope that is home and dry. Let's continue. Number 2, question number 2. Question number 2. The speed of a wave in deep water depends on its wavelength L. Now wavelength is a length. And the acceleration of free fall G. So the speed of a wave is depending on its wavelength L, and it is depending on the wavelength L and the acceleration of free fall G. So the question is, what is the possible equation for the speed V of the wave? Of course, the question will not directly ask you to derive the units or to check which equation gives the most appropriate units for speed. But as if you have studied the base units, you can check which of these equations has units as meters per second squared, because you and me know that the appropriate units for velocity or speed will be actually meters per second squared. Note that, not per second squared, meters per second. I want you to note that I rarely use equal signs on units because it doesn't make any sense to put equal signs on units. Let's check the first one. What are the base units here? The base units for in A, the base units would be G is acceleration due to gravity. We have already seen that the base units of acceleration are meters per second squared. Then times L, which is meters. This becomes meters per second squared. Okay, this is meters squared per second squared. But because of the square root, this is raised to power half. This boils down to meters per second. We know that this is the SI unit for speed. So most likely this could be a possible equation for the speed of V of the wave. We can check the others. For B, this was for A. For B, G is meters per second squared, L is meters. This would give a unit as meters squared s power negative 2. This is not a unit for speed. So it means we cannot accept B. We can check C. G is meters per second squared divided by L, which is meters. This would give us a seconds power negative 2. Of course, when you find a square root, because there is a square root, it becomes seconds power negative 1. This is not a unit for speed, so we cannot accept this equation. The last equation, we have meters per second squared divided by meters, which becomes seconds power negative 2. This is not a unit for speed, so this is also a wrong equation. So we accept that A would be the possible equation for the speed of a wave. Okay, thank you for watching that. I hope we can now proceed to the next question. Question number 3. Question number 3. Here we have a simple question. Which expression gives an SI base quantity? SI base quantity. A is charge per unit time. B is force per unit area. C is mass per unit volume. And D is work done per unit distance. So they are saying which expression gives an SI base quantity. An SI base quantity. So this one is charge per unit time. Time is of course a base quantity, but how about charge? This is force per unit area. Of course, force is not a base quantity, even though area can be length and length. Then we have mass per unit volume. Mass is a base quantity, and the volume is one length times another length times another length if it is 3 dimensions. Therefore, this could be the expression which gives an SI base quantity, because This volume is just L cubed. So this will be mass over L cubed. And this will be a force over L squared. This would be a charge over T. This will be a work done is force over distance, which is L. So we can agree that mass per unit volume would give an SI base quantity. Mass per unit volume would give an SI base quantity. Next, question number 4. The frequency F of vibration of a mass m supported by a spring with a spring constant k is given by the equation F is equal to Cm power p k power q and k power q, where c is a constant with no units. What are the values of p and q? So this appears as if it is a hard question, but I want to assure you that this is a very easy question. Here we are now going to employ the concepts of homogeneity that we learned in class. If we want a power or we want powers of these quantities, we must equate now the base units on both sides of the equation. F is the frequency. Let's see what are the base units of frequency. F is of course 1 over t, 1 over period, which is the reciprocal of period, and since period is a time, so the units are seconds. So the base units of frequency will therefore be 1 over second, which is s power negative 1. Then they have defined this m as mass, so the base units of mass are actually kilograms. Then they have defined k is a constant, given by that equation, where c is a constant with no units. So they have said c has no units, so we shall not bother about c. So we are now going to simply equate these quantities. We are going to equate these quantities. They said the spring with a spring constant k. Before we equate, let's find the base units of k. From Hooke's law, the force is directly proportional to the extension x. So the force is equal to the spring constant times x. So k is going to be the force divided by the extension. We know that extension, the base units will be meters because it is a distance or a length. Then we have already seen that force is mass times acceleration. So this will be mass, kilogram, acceleration, meters per second squared. So it implies that the base units of k will be those of force, which are kilogram meters per second squared, divided by extension, which are meters. So it means the base units of k will actually be kilogram per second squared. Kilogram per second squared. Those will be the base units of k. Now let's equate the units. Therefore, for f, we have s power negative 1. This will be equal to c has no units, so I will not include the units here. I can't even waste time putting there 1. Then m, that is kilogram, that is raised to power p. And k is kilogram per second squared. This is raised to power q. So I will simply to find the p, or it is easier to start with q, maybe. So this side I have s power negative 1. The other side I will have s power negative 2 times q. So that will be negative 2q. So this implies that negative 2q is equal to negative 1. So q is going to be equal to a half. Q is a half. Okay, then next, since this side I don't have kilograms, I will maybe say kilogram power 0, because anything to power 0 is 1. Then this will be equal to this side I have kilogram power p, and I also have kilogram power q. So it becomes p plus q, we add the powers. So it means P plus Q should be equal to 0, but remember Q is already a half. So P plus a half should be equal to 0, which means that P should be equal to negative a half. So we have solved for P and we have already solved for Q. I hope I have made this extremely clear. Let's continue. Question number 5. The energy E transferred when charge Q moves through an electric component is given by the equation E is equal to QV. Remember, E has been defined as energy and Q has been defined as charge. V is actually the potential difference. I think we define potential difference as the energy converted from electrical to thermal energy per unit charge. So I think that formula is actually, we are familiar with it. So use the equation to determine the SI basis of potential difference. So I just simply make V the subject. V is going to be equal to E divided by Q. Remember, Q is defined as charge. So the basis of charge, because charge is current times time, the basis of charge are actually going to be ampere times seconds. Then I have E. E is energy. I think I can use any formula for energy, whether it is kinetic energy, whether it is potential energy, whether it is elastic potential energy. I know it will give me the correct base units of energy. I can also think about energy as work done, because work done is actually energy in motion. So let me use the simplest. I will use energy to be equal to potential. I can even use potential for simplicity, because the quantities in this expression for potential energy are easy to find their base units. So I could use energy to be equal to work done, which could be force times distance in the direction of the force. Or I could use the expression for energy as kinetic energy, a half mv squared. Or any of these expressions could give me the expressions for energy, but I will concentrate on the first expression. So M is mass, base units kilograms. G is acceleration due to gravity, base units meters per second squared. H is a length or a height, which is meters. So the base units of energy are going to be kilograms, meters per second squared times meters, which simplifies to kilogram meters squared per second squared. When you advance and you become an expert, some of these units become part of you that you don't show every step in the working. Therefore, I'm saying that the base units of V will be equal to the base units of E, which are kilogram meters squared per second squared, divided by the base units of Q, which are ampere seconds. When we simplify this, we shall see that kilogram meters squared, when ampere goes up, it becomes per ampere. When S goes up, it becomes S power negative 3, because we subtract the powers. These will be the base units of the potential difference. I think that is also home and dry. That is very simple. Let's continue. Oh, sorry, I have to go back to question number. Question number 6. Question number 6. Use an expression for work done. Here we are now very specific to show that the SI base units of energy are that. So work done is energy in motion. So energy is going to be equal to work done, which is equal to the force times the distance, but this is distance in the direction of the force. Maybe you can call it the displacement. The base units of distance are going to be meters. The base force is equal to mass times acceleration. The base units of force will be those of mass, which are kilogram. and the base units of acceleration will be meters per second squared. And when we combine, it means the base units of energy will be those of force, which are kilogram meters per second squared, times the base units of distance, which are meters, and this simplifies to kilogram meters squared per second squared. Note that I am always trying to avoid putting equal signs on the units or between the quantity and its units. But I put equal signs when I simplify the quantity further, because the equal signs are just implying simplification in this case. So to me, it doesn't make sense when you put equal signs on a quantity. How does it look when you say, okay, F equals kilogram meters per second squared? To me, it doesn't make any good sense. That's why you just use these kind of colons for stating the units. Let's continue. Question number 6. The energy E stored in an electrical component is given by E is equal to Q squared over 2C, where Q is of course defined as the charge and C is a constant. We are not sure whether it has units or not. Use the equation and the information in part A to determine the SI base units of C. It means question 5 is part of this. It is the part A of this question. So in question number 5, we have already seen that the base units of in question, what question was that? Was it number 6? Oh, sorry, this is a continuation of number 6. I had not seen this. So question 6, we had already seen that the base units of energy, are kilogram meters squared per second squared. So we are going to use this to solve this part of the question. Remember, Q is charge, so the base units of Q squared are going to be ampere squared seconds squared. Then C is a constant, and it's the quantity whose units we want. So we are making C the subject here. You notice that when I make C the subject, C will be equal to Q squared divided by 2 times E. You always notice that when I'm writing the base units, I don't include such coefficients or constants. So I can't include 2. So since I have the base units of each quantity I need, so I will simply say that the base units of C are going to be those of charge, which are ampere squared seconds squared divided by those base units of E, which will be kilogram meters squared per second squared. I know some of you will always continue adding or putting these coefficients in the units, but it doesn't make any sense. In fact, it will leave you even confused. The coefficients cannot be put in the units, but of course the power affects the units. That's why you see it was Q squared and I squared the units. Okay, so if you want to simplify this, you could say taking kilograms up, it becomes per kilogram. Taking meters squared up, it becomes per meter squared. Of course, ampere squared is remaining. And taking s power negative 2 up, we subtract the powers. So it will be s power 2 minus negative 2, which becomes s power 4. So this will become s power 4. So these will be the base units for the quantity C. I hope that is home and dry. That is very simple. Let's go to the next. Question number 7. The dragger force Fd, so Fd is defined as force, acting on a car moving with a speed v, so v is the speed, on a straight horizontal road is given by this expression, where k is a constant and a is the cross-sectional area, so a is actually area of the car. Determine the SI base units of k. So to begin with, I'll make K the subject because it's the quantity whose base units I need. So I will say K is equal to the drag force Fd divided by V squared times A. I hope I have made A the subject, I mean K the subject. So to begin, I will begin with the simple quantities. V squared, V is speed. The base units will be meters per second, but this is squared because V is squared. Then A is cross-sectional area. The base units of area are meters squared. And also we have F, the drag force Fd. Remember, force is mass times acceleration. So mass is kilograms, acceleration is meters per second squared. So all that remains is to combine these quantities into the base units of K. So the base units of K will be equal to the base units of force, which are kilogram meters per second squared, divided by V, which is meters. Now I'm squaring V, it becomes meters squared, S power -2, times area, which is meters squared. When we simplify, so we have kilogram in the numerator. You have meters divided by meters squared times meters squared. In other words, you have meters, mathematics window here, meters divided by meters power 4. We subtract the powers. And when we subtract the powers, it becomes meters power 1 minus 4, which becomes meters power -3. So this would be m power -3. Then we have s power -2 divided by s power -2, which becomes, of course, that becomes 1. So that one will disappear. Therefore, I basically remain with only this expression here for the base units of K. And I think K, because these are base units of density, perhaps K is density. Okay, let's continue. Question number 8. Question number 8. The drag coefficient CD. The drag coefficient CD. The drag coefficient CD is a number with no units. It is used to compare the drag on different cars at different speeds. So CD is a number with no units. We don't mind about that. And CD is given by that expression. Where F is drag force, rho is density, A is cross-sectional area of the car, and V is speed. What is the value of N? So because we want N and N is a power, all we shall do is to equate the base units. But to make this one look a little bit simpler, I will begin by cross multiplying. So I will say the drag force, the drag coefficient CD is going to be multiplied by V power N times density times cross-sectional area being equal to twice F. Remember, CD has no units, but V is speed. Its base units will be meters per second. Rho is density. Its base units are kilogram per meters cubed. A is cross-sectional area. Its base units are meters squared. And F is force, drag force, that is mass times acceleration. So this will be kilogram meters per second squared. Now I can equate the base units. If I try to equate the base units now, remember CD has no units, so I will not mind about it. I'll begin with V, which is meters per second, but this is raised to power N. Then density, so I will say times kilogram per meter cubed. Then I will say times cross-sectional area, which is meters squared. This should be equal to kilogram meters per second cubed, per second squared. So I will just take N, I will just take a quantity which has N. This side, I can take M. So this side I have M power N, then times M power -3, then times m power 2. The other side I only have m power 1. So we add the powers when we are multiplying quantities. So this becomes m power n plus negative 3 plus 2 is equal to m power 1. So this is m power n minus 1, which is equal to m power 1. So we equate the powers, n minus 1 is equal to 1, which means that n is equal to 2. So the value of n required is actually 2. So this is actually, we have used the homogeneity. We have just equated the base units on both sides of the equation. Okay, let's move to the next equation. I hope that one is home and dry. Let's move to question number, is it question number 10? Oh, question number 9 is skipped, but that's fine. Question number 10, question number 9 is skipped, but that's fine, it is not there. Question number 10 is asking us to determine the SI base units of stress. Now, just to give a simple background, stress, in the formation of solids as a unit, you study stress, strain, and Young's modulus. And I think you use the symbol sigma for stress, and you define stress as the force per unit cross-section area. You'll use epsilon for strain, and you define strain as extension over original length. And of course, you use maybe, sometimes you use E. Instead of that, you normally use E for Young's modulus, which is stress divided by strain. So let's straight away go to the SI base units of stress. By definition, stress is going to be defined as force over cross-sectional area. So using symbols, stress is going to be defined as force over cross-sectional area. The base units of area are meters squared. Then force is mass times acceleration. So the base units of force will be those of mass, kilogram, and then acceleration, that is meters per second squared. So the base units of stress will therefore be equal to those of force, that is kilogram, meters per second squared, divided by area, which is meters squared. And when you simplify meters divided by meters power 2, remember the mathematics window where we subtract the powers, meters over meters squared is the same as meters power 1 minus, actually minus 2, we subtract the powers. Therefore, this gives you meters power negative 1. So we are saying that this becomes kilogram, meters power negative 1, seconds power negative 2. And when you become an expert, you will realize that even pressure has the same base units. Therefore, this could be an equivalent unit to the Pascal. So that is stress. That is stress. Let's continue. Part B, determine the SI base units of resistivity. Determine the S. I don't know whether I skipped over, but I can try to go back. Okay, I didn't skip any. Determine the SI base units of. Determine the SI base units of resistivity. Resistivity. Okay, I think this is the longest or the most complex question in deriving base units, but we can still find this easily. So to begin with, maybe I've remembered one student told me the color red is not good to him, so I can change. Let me use purple. So resistivity. We know from electricity, we know that resistance is actually directly proportional to length and inversely proportional to cross-section area, and the proportionality constant was the resistivity. So resistance was given by rho L over cross-section area A. But then um, you could still find the Bayesians of rho, making rho the subject. Rho will be equal to R times A over L. It is easy to establish the Bayesians of cross-sectional area as meters squared. It is easy to tell the Bayesians of L as meters. The only challenge are the Bayesians of resistance. We can use, there are several expressions where we can find resistance. Number one, we can see from Ohm's law that V equals to I times R. V is I times R, and making R the subject, or maybe I can use power is equal to I times I squared times R. I think this is the shortest. Power is I squared times R because I know power is the rate of doing work or the rate at which energy is transferred. So making R the subject, R will be equal to power over I squared. I could still use this, but this would be taking me some more time, but still this takes me to this. So the Bayesians of I squared, because that is current, that will be meters squared. Then I know power is the rate of transfer of energy, so that is energy over time. At this level, I think energy can be work done, because work done is energy in motion. At this level, if you are an expert, I think the units of energy have already become part of you. The Bayesians of energy are kilogram meters squared per second squared. So it means the Bayesians of power will be energy, which is kilogram meters squared per second squared divided by time, which is seconds, which simplifies to kilogram meters squared per second squared divided by seconds, that is seconds power negative 3. That is power. That means the Bayesians of resistance will be equal to power, which is kilogram meters squared s power negative 3 divided by current, which is going to be, how did I put current as meters squared? Sorry. Current cannot be meters squared. This is ampere squared. That was a slip of the tongue. So this is divided by amperes squared. So when you simplify, the Bayesians of resistance are kilogram meter squared per second cubed per ampere squared when this goes up. So now we have the Bayesians of resistance. It becomes easy to find the Bayesians of resistivity. The Bayesians of resistivity will be those of resistance, kilogram meter squared, second power negative 3 per ampere squared, then multiplied by area, which is meters squared, divided by length, which is meters. Simple algebra, kilogram has remained. Here I have meters squared times meters squared divided by meters. It becomes meters power 3. Here we add the powers and then we subtract 1. Then S power negative 3, amperes power negative 2. So those will be the Bayesians of resistivity. Okay, let's continue. The Bayesians of resistivity are done. The only challenge is arriving at the Bayesians of resistance. If only you can choose a method to arrive at the Bayesians of resistance, then it becomes literally very easy to obtain the Bayesians of resistivity. Next, so we have done with that. Next is number 11. Question 11, the maximum theoretical power, so P is power, of a wind turbine is given by this expression here. The maximum theoretical power is given by that expression. So rho is density, A is area, V is speed, K is a constant with no units. What is the value of N? Because N is a power, we are going to equate the base units, that is, we are going to use homogeneity. We have already seen that the power is the rate of transfer of energy, that is energy per unit time. But we know the base units of energy as kilogram meters squared per second squared. So the base units of power are now known as kilogram meters squared per second squared divided by seconds, which simplifies to kilogram meters squared s power negative 3, that is for power. The base units of density is kilograms per meters cubed. Then cross-sectional area, that is meters squared. Speed, that will be meters per second. Now we substitute, or we equate the base units on both sides of the equation. So on the left, I have kilogram meters squared per second cubed. On the right, k has no units, I will not include it here. So I have kilogram per meters cubed times meters squared times meters per second, but this is raised to power n. So I need n. I can choose any of these quantities, raise it to power n, and I bring it, and I also choose it this side. So this side I can use s power negative 3. The other side I have s power negative n, because it is power negative 1 but raised to another power. Mathematically, a power raised to another power, you multiply the powers. So n is actually equal to 3. Alternatively, I could use m. On the left I have m power, on the left I have m power 2. On the right I have m power negative 3 plus 2 plus n. Add the powers when we are multiplying. Now this is m raised to power n, that's why I have added n there. So equating the powers, we have 2 is equal to, this is negative 1 plus n, negative 1 plus n, which also implies that n is equal to 3. So I have solved for n. I hope that is home and dry. That is very simple. Let's continue. Let's continue to question number 12. Question number 12. All bodies radiate energy. The power radiated, so P is standing for power, radiated by the body is given by this expression. T is thermodynamic temperature. Remember, thermodynamic temperature is one of the basic quantities whose units are kilograms. A is surface area. K is a constant. Determine the SI base units of K. So if we want to find the base units of a quantity, we make it the subject. Therefore, we shall say that K is equal to, I'm making K the subject, that will be power divided by area T power 4. If you have studied cosmology and astrophysics, I think that expression comes into your mind as that expression must be something I've already seen in A level. That is, I think that is in the astrophysics, when you are looking at Wayne's displacement law, Stefan Boltzmann's constant, and so on and so forth. And actually, it is Stefan Boltzmann's constant. So P is power. We have already seen that the base units of power at this point, they are now part of U. Kilogram meters squared per second squared for energy, divided by time, which is seconds, which simplifies to kilogram meters squared per second cubed. That is for power. A is cross-sectional area. The base units of A are meters squared. T is thermodynamic temperature. The base units of T are Kelvin, capital K. Now we find the base units of small k, not the difference. So the base units of K will be those of power, kilogram, meters squared per second cubed, divided by area, meters squared, times K times Kelvin, but Kelvin is to power 4. Kelvin is to power 4. This therefore simplifies to kilogram. Of course, this one is cancelling with that one. So it becomes kilograms S power negative 3. When K goes up, it becomes Kelvin power negative 4. Those will be the base units of small k. Okay, so I hope that is also home and dry. Next. Question 13. Question 13 is basically, it's actually directly Stefan Boltzmann's law. The luminosity L of a star is given by that expression. Remember, luminosity is the total radiant power emitted by an object. If we are talking about luminosity of a star, then we are referring to the total radiant power emitted by that star, or the total energy radiated by a star per unit time, that is its luminosity. So the luminosity of a star is given by that expression. R is the radius. The base units of R are meters. T is temperature. The base units of T are Kelvin. Sigma is a constant with units watts per meter squared per Kelvin. Now notice that per meter, that is SI, per Kelvin, that is SI, but watts is not base units. Watts is not base units, so we have to change the watts. But the watt is an SI unit of power, and power, we have already seen the base units of power earlier on because it is energy per unit time. So the watt is equivalent to the base units of power, which are kilogram meters squared per second power negative 3. That is the watt, because the watt is the unit of power and power is energy over time. So that is the equivalent unit for the watt is that. Therefore, we shall say that the base units of sigma will be kilogram meters squared seconds power negative 3 times meters power negative 2 times Kelvin power negative 4. When you simplify this, I just take all these quantities here so that I simplify at once. So the base units of L will be, I ignore the constant for pi, so R is squared, so it is meters squared times sigma, which is going to be kilogram meters squared S power negative 3 times meters power negative 2 times Kelvin power negative 4. Then again times T power 4, which is times K power 4. Some of these quantities have already cancelled. So like this one cancels with that one because it is K power 0, which is 1. This one cancels with that one because this will be M power 0, which is 1. Therefore, this simplifies to kilogram. I'm remaining with the meters squared S power negative 3. So that will be the luminosity. Those will be the base units of the luminosity of a star. Those will be the base units of the luminosity of a star. I think I've tried my level best to make it understandable. Okay, let's continue to our next question. Let's continue. So next is question number 14. Next is question number 14. The stress sigma needed to fracture a particular solid is given by that equation. So sigma is standing for stress. Then E is called the Young modulus, D is distance, K is a constant with no unit, so it will not bother us much. What are the SI base units of gamma? So because we want base units of gamma, we make it the subject. So I am going to square both sides. Squaring both sides, so you have sigma equals to K square root of gamma E over D. I'm squaring both sides I'm trying to make sigma the subject. I mean gamma the subject. So this side also squared. I will have that sigma squared is equal to k squared, the square root has cancelled, so I have gamma E over D. Making gamma the subject, gamma is going to be sigma squared times D divided by k squared times k squared times E. I think that is gamma. I've made gamma the subject. Now I can list the base units. I will start with the simplest. D is distance. The base unit is meters. K has no units, so I will ignore. I will say K has no units. Do not affect anything. Then E is Young modulus. E is Young modulus. E is Young modulus. Sigma is stress. Maybe let me begin with the sigma. So sigma is a quantity, or sigma is force over area. We have already seen that the base units of stress are kilogram, meters power -1, s power -2, because it is kilogram meters per second divided by meters, which gives you that. So I now have the base units of sigma. Young modulus is defined as stress over strain, which is force over a cross-sectional area divided by extension of original length, which becomes original length divided by extension. Of course, the base units, because original length, base units are meters, extension, base units are meters. So this strain does not affect the units of Young modulus. It is only force over area which determine the units of Young modulus. So you will notice it is almost the same as this. So the base units of Young modulus will be the same as stress, that is kilogram per meter per second squared. So we now go back. The base units of gamma will be those of Young modulus, stress, kilogram per meter per second squared, but this should be squared, times D, which is meters, divided by Young modulus, which is kilogram per meter per second squared. So this one cancels that square. So you now remain with kilogram per meter per second squared times meters, which now becomes kilogram per second squared. Kilogram per second squared. Because m power -1, when I multiply it with m, it cancels out. Therefore, you remain with only that constant, that quantity there. So those will be the base units of gamma. And I hope that is also understandable. Let's continue. Number 15. Number 15. Number 15. I'll be first on this question. Number 15. The force F is defined as the force. Point charges Q1 and Q2. So Q1 and Q2 are charges. Distance R apart. R is distance. What are the SI base units of K? So I begin very first, make K the subject. So K is going to be F times R squared divided by Q1 times Q2. So I can now list the base units. Base units of F, that is kilogram, meters per second squared, because it's mass times acceleration. Base units of R, that is meters. Base units of Q1 or Q2 will be ampere times seconds, because that is charge. So the base units of K will be those of force, which is kilogram, meters per second squared divided by, or times R squared, that is meters squared, divided by Q1 is ampere seconds, Q2 is also ampere seconds. We now simplify. So this will be kilogram, meters times meters squared becomes meters cubed. Then s power -2 in the numerator divided by s squared in the denominator becomes s power -4. Mathematics window, s power -2 divided by s times s. That becomes s power -2 minus 2, because in the denominator s times s is s power 2. So it becomes s power -2 minus 2, which becomes s power -4. Then we have in the denominator we have ampere times ampere, which is ampere squared. When it goes up, it becomes per ampere squared. So those will be the base units of K. Okay, let's proceed. I hope that was easy. Question number 16. Question 16. The speed V is speed of sound in a gas, is given by that expression. P is pressure, rho is density, gamma is a constant. What are the SI base units of gamma? So to begin with, I will make gamma the subject by squaring both sides. I square this side, I square the other side. So I have that V squared is equal to gamma times pressure divided by rho. So I want gamma, so I make gamma the subject. Gamma is going to be equal to V squared times rho divided by P. I now list my units. V is speed, units meters per second. Rho is density, units kilogram per meters cubed. P is pressure, pressure is force over area, which becomes now kilograms per meter per second squared, because force is mass times acceleration divided by mass. So it becomes kilograms per meter per second squared. So we now have pressure, we have density, we have V. So all we need is the units of gamma. So that will be meters per second, but remember this is squared, times density, which is kilogram per meters cubed, divided by pressure, which is kilogram per meter per second squared. So we simplify this. I'm trying to simplify so that I come up with the correct units. Kilogram has cancelled. Immediately there is kilogram and kilogram. So this one has already cancelled out. Now I have meters per second. Okay, let me simplify this further. I have meters squared seconds power negative 2 times meters power negative 3 divided by meters power negative 1 s power negative 2. S power negative 2 has also cancelled. So you notice I remain with m power negative power 2 times m power negative 3. We add the powers. So this means I will have meters. This means I have meters power negative 1 in the numerator divided by meters power negative 1 in the numerator. So we have m power negative 1 in the numerator because we add the powers, and m power negative 1 in the denominator. So actually, you realize that it's like all the units have cancelled out. So we conclude that gamma has no what? Gamma has no unit. Gamma has no units. Okay, next. Let's go to number 17. Number 17. Gas flows through the narrow end of a pipe. Under certain conditions, the mass m of the gas flows through the nozzle in a short time t. The mass that flows through the nozzle in a short time t, so t is time, is given by that expression. Remember, m is mass, t is time, k is a constant, no units. So k, no units, do not bother us. C is a constant which depends on the nozzle size. Rho is density. P is pressure. Determine the SI base units of C. So straight away I'm going to make C the subject. Sorry is my sorry is a good my what? Sorry is my advice to students to always make that quantity the subject before you substitute the units. So making C the subject, C will be equal to, that will be m over T divided by K square root of density times pressure. There was no need for me to break down m over T anyway. So m over T, the base units of m over T will be mass, that is kilogram, divided by T, that is kilogram per second. Then, of course, K has no units. Rho is density, that is kilograms per meters cubed. P is pressure. Pressure is force over area, which is kilograms per meter per second squared. So now I can substitute. The base units of C will be kilogram per second divided by kilogram per second divided by the square root, or divided by, I will just use power half. So this will be kilogram per meters cubed times kilogram per meter per second squared, but this is raised to power half because of the square root. Let's try to simplify this and see what happens. So in the numerator we have kilograms per second still divided by, in the denominator we have kilograms squared, and meters power negative 3 times meters power negative 1, that is meters power negative 4. Then s power negative 2, but this is raised to power half. So it's like we find the square root of each of these. When we find the square root, we still have kilogram s power negative 1 divided by, so kilogram squared becomes kilogram, m power negative 4 becomes m power negative 2, s power negative 2 becomes s power negative 1. So you notice also that kilogram has cancelled the kilogram, s power negative 1 has cancelled, so you are remaining with 1 over m power negative 2. And when you simplify this, it becomes m power positive 2, the reciprocal of that. So it means the base units of C are going to be m power 2. Okay, so that requires resiliency, and I hope that is understandable. Next, example number 18. Example number 18, the average kinetic energy. The average kinetic energy, we shall see this expression in ideal gases, in a unit called ideal gases, or you must have seen it in a unit called ideal gases. So energy is given by that expression. T is absolute temperature, units Kelvin. Find the base units of K. I just make K the subject. So K is going to be equal to, I'm making the subject, so it will be twice E over 3 times T, the denominator. Twice E over 3 times T. T is thermodynamic temperature, the units are capital K, Kelvin. E is energy. We have already seen that energy is kilogram meter squared per second squared. So the base units of K will be, I ignore the constant 2 over 3. This will be ignored. So this will be kilogram meter squared per second squared divided by Kelvin. And when we simplify this, it means the base units of K will be actually kilogram meters squared per second squared per Kelvin. Those will be the base units of K. Those will be the base units of K. Let's continue. Let's continue to question number 19. Question number 19. What is the joule in SI base units? What is the joule in SI base units? So it appears as if the student will be wondering now, what am I deriving? One, of course, you know that the joule is a unit of energy. The joule is a unit of energy, and energy is work done. Any other formula for energy should give you the base units equivalent to the joule. So The joule is a unit of energy, and energy can be any formula for energy. I would prefer to use the simplest, mgh. So the base units of energy, which is the joule, the SI unit of energy, which is the joule, is equivalent to the base units of energy, which are kilogram for mass, meters per second squared for acceleration due to gravity, times h. Times h. Sorry, this will be not h, it is in meters, it is m. Because h is in meters, it is a length. So we have to put the m. Then when you simplify, it becomes kilogram meter squared per second squared. So it means the joule is equivalent to kilogram meter squared per second squared. As simple as that. Okay, next. So let's move to question number 20. Question 20. Question 20. Oh, my power is running out. So can question 20. Question 20. The speed v of a sound wave through a gas of density ρ and pressure P is given by that expression, where C is a constant, and show that C has no units. Immediately we make C the subject, so I square both sides. I'm squaring both sides. When I square both sides, I will have that V squared is equal to C times pressure over ρ. When I make P the subject, I want C, so I will make C the subject. C will be equal to ρ times V squared over P. Rho is density, base units kilogram per meters cubed. V is speed, base units meters per second. And then P is pressure. We now know that pressure is kilogram per meter per second squared. So we just simplify, we just substitute. The base units of C will be density, kilogram per meter cubed, times speed, meters per second. But remember, this is squared. Divide by pressure, which is kilogram per meter per second squared. When we simplify the numerator, we have kilogram. Meters power negative 3 times meters squared becomes meters power negative 1. Then S power negative 2. Then divide by kilogram m power negative 1 times s power negative 2. So we notice that the quantities are actually looking alike. So I will cross out term by term, term by term, term by term, and I will conclude that C has no units. You conclude that C has no units. You cannot equate this to 1 or 0. It doesn't make any sense. So you just cross out the terms and conclude that C has no units. As simple as that. Okay, next. Next is question number 21. Question number 21. The Reynolds number R is a constant used in the study of liquids flowing through pipes. R is a number with no units, so R has no units. We shall not bother about it. Rho is still density, V is speed, D is diameter, which is a length. What are the SI base units of mu? We make mu the subject very fast, so mu is going to be equal to density times V times D divided by R. Remember, R has no units. Base units of density, kilogram. This is kilogram per meters cubed. The base units of diameter, this will be meters. The base units of speed, this will be meters per second. So the base units of mu will be density, that is kilogram per meters cubed, times V, which is meters per second, times diameter, which is meters. Of course, R has no units, so I will not include it there. When I simplify this, I have kilograms, meters power negative 3 times meters times meters. It becomes, I think, meters power negative 1, then S power negative 1. So this will be the base units, or this will be the base units of mu. I think mu would be viscosity or viscous drag, something like that. Okay, next. Next is number 22. Number 22. Number 22. At temperatures close to 0 Kelvin, the specific capacity C of a particular solid is given by that, where T is thermodynamic temperature, B is a constant characteristic of the solid. The SI unit of specific capacity is joules per kilogram per Kelvin. What is the unit of constant B expressed in SI base units? So C is a constant, sorry, C is the specific capacity, and we want the SI base units of B. Let's make B the subject very fast. B is going to be equal to C divided by T power 3. And C has these units. T is temperature, which is in Kelvin. C specific capacity, which is the joules per kilogram per Kelvin. But remember, the joule is equivalent. The joule is actually equal to, because it is energy, that is kilogram meter squared per second squared. So we now combine. Let's simplify this. So that means we shall just say that the base units of B will be specific capacity, which will be kilogram meter squared per second squared for the joule, times per kilogram times per Kelvin, divided by T power 3, which is Kelvin power 3. When you simplify, you remain with kilogram meter squared S power negative 2. So you have, oh, kilogram has cancelled. So per kilogram and kilogram have cancelled out. I had not seen that. So this kilogram has cancelled out. So you have meters squared S power negative 2. Then Kelvin power negative 1 divided by Kelvin power 3 becomes Kelvin power 4. It becomes Kelvin power 4. So that implies that these will be the SI base units of B. Those will be the SI base units of B. The only challenge was, the only trick was changing joule, removing the joule because it is not SI. It's not an SI base unit. Okay, number 20. Question 23. Question 23. Question 23. The time taken, so T is time, for a satellite to orbit the Earth on a circular path is given by this equation. R is radius, M is mass, K is a constant. What are the SI base units of K? Straight away we make K the subject. So K is going to be equal to T squared times M divided by R cubed. R is radius, the base units of R meters. M is mass, the base units kilograms. Then T is time. T is time, the base units are seconds. So we substitute. The base units of K will be T, which is seconds squared, times M, which is kilograms, divided by R, which is meters squared. I mean meters, but cubed. So this simplifies to kilogram second squared per meters cubed. Those will be the base units of K. I think that is now very easy. Let's go to question number 24. Question number 24. Question number 24. The rate of flow of thermal energy Q over T in a material is given by Q over T is equal to CAT over X. So Q over T, this time Q is not representing charge. You must note that very carefully. A is cross-sectional area, T is temperature, X is thickness, C is a constant. So they want the Bayesians of C. We begin by making C the subject. So C is going to be Q over T. I don't need to convert to split this, times X divided by A times T. Now X is thickness. The Bayesians of X are meters. A is cross-sectional area, that is meters squared. And then T is thermodynamic temperature, that is Kelvin. Then Q over T, that is energy per rate of flow of energy, that is energy over time. Remember, energy is kilogram meters squared per second squared. Over time, it becomes kilogram meters squared per second power negative 3. That is energy over time, because Q is standing for thermal energy. Now, when we simplify, we now substitute in that equation. So the Bayesians of C will be kilogram meters squared per second cubed times meters divided by meters squared times T is Kelvin, so times Kelvin. Okay, so when we simplify this, I think this can cancel with that one. So you remain with the kilogram meters per second cubed per Kelvin. So those will be the Bayesians of C. I hope the algebra is simple. Let's continue. Number 25. Question 25. Question 25. The potential energy, so EP is standing for potential energy, in a stretched wire is given by that expression. Sigma is strain, C is a constant, V is volume. What are the Bayesians of C? We make C the subject straight away. So C is going to be equal to E potential times 2, there is a 2 there, divided by sigma squared times V. Remember, V is volume. The Bayesians of V will be meters cubed. Then EP is potential energy. We have already seen the Bayesians of energy are kilogram meters squared S power negative 2. And then sigma is strain. Strain is extension of original length. So strain has no what? No units. Because extension is in meters, original length is in meters. Therefore, we can substitute and say the Bayesians of C will be energy, that is kilogram meters squared per second squared, divided by sigma, which has no units but squared, so it doesn't affect anything, over meters cubed. So when I simplify this, this becomes kilogram m squared over m cubed, that is m power negative 1 s power negative 2. So those will be the Bayesians of C. Okay, number 26. Question number 26. Question number 26. 26, the speed of, so V is speed of a liquid leaving a tube depends on the change in pressure. So change delta P is change in pressure, and the density rho is density. The speed is given by that expression where K is a constant that has no units. So K has no units, so we shall not mind about it much. What is the value of N? So since N is a power, we are going to use homogeneity. We are going to equate units. We are going to equate the units since N is a power. So we have Bayesians of V. V is speed, that is meters per second. We have rho is density, that is kilogram per meters cubed. We have P or change in pressure. Pressure is force over area, which will be kilogram per meter per second squared. Now we equate the units on both sides of the equation. On the left, I have meters per second equals to, K has no units, I will ignore it. This will be kilogram per meter per second squared for pressure, change in pressure, divided by kilogram per meters cubed for density. This is all raised to power n. Of course, you can, if you want, you can simplify this. You can simplify this, but I'm interested in n, so I can just pick a quantity which has n. I can say take s. So s power negative 1 on the left is going to be equal to s. S power negative 2 raised to power n becomes power negative 2n. So you will notice that n is equal to a half, because we equate the powers. Negative 1 equals to negative 2n. N becomes a half. Alternatively, I would also have taken m. M power 1 on the left is equal to, on the right, I have m power negative 1 divided by m power negative 3. You subtract the powers. M power negative 1 minus negative 3 becomes m power 2. Yes, you subtract the powers. But again, it is raised to power n. So it becomes m power 2n. That means when I equate the powers, still n becomes a half. So I have found n. Next is question number 20. Question number 27. Question number 27. Question number 27. A mass m, so m is mass, placed on the end of a string that is hung vertically as shown. So the mass is placed at the end of the string and is hung as shown. The time period of the oscillation of the mass is t, so t is time. The period is given by that. Okay, so I think the question continues on the next slide. The question continues on the next slide. C is a constant and K is the spring constant. Show that C has no units. Show that C has no units. So that is question 27 continued. So we have been given that T is equal to C square root of M divided by K. C is a constant and K is the spring constant. Show that C has no units. So one, we can begin by finding the units of the spring constant from Hooke's law. The load is equal to a constant times the extension. So it means the constant is equal to the load over the extension. So the base units of K are force, kilogram, meters per second squared, divided by meters, which means the base units of K are kilogram per second. That one we have already established. And then we make C the subject. Squaring both sides, we have T squared is equal to C squared into M over K. So I want C. So I find C, I make C the subject, so it becomes C squared is equal to T squared divided by, or if you want to take K up, so times K over M. Alternatively, I would just, why do I waste time? I would have just made C the subject here by simply saying that C is equal to T divided by the square root of M over K without even breaking it. So when I substitute quantities, remember T is time. The base units of T were seconds. So the base units of C will be time, which is seconds, divided by the square root of M M was mass, which is kilograms, divided by K, which is kilograms per second squared. We are trying to simplify now, so it becomes S over the square root of kilogram has already cancelled. I now have 1 over S power negative 2, which is when I get the reciprocal, it becomes S over the square root of S squared, which therefore implies that I have S over S. These are also cancelling out. So I conclude that C has no what? No units. I'm emphasizing, please do not say equals to 1. It will not make any sense. You can't say equals to 1. Just conclude has no what? Has no units. Okay, next. Next is question number 28. Question number 28. The figure shows a turbine that is used to generate electrical power from the wind. So we have a turbine used to generate electrical power from the wind. This question continues. The power P available from the wind is given by that expression. L is length, rho is density, V is speed, wind speed, C is a constant. Show that C has no units. Show that C has no units. Okay, so the power available from the wind has been given by this expression here. So we want to show that C has no units. I think the easiest thing to begin with is to make C the subject. So making C the subject, we see that C is going to be equal to the power divided by L squared density times V cubed. So since L is length, the base units of L will be meters. V is speed, the base units of V will be meters per second. And so that is V. And then rho is density, the base units will be kilogram per meters cubed. So we are going now to simply substitute, but we have power. I think by now the base units of power are part of us. Power will have base units as kilogram, meters. For energy it is meters squared per second squared, but when you divide by time to get power, it becomes S power negative 3. Therefore, we are now saying that the base units of C will be equal to those of power, which will be kilogram meters squared S power negative 3 divided by meters squared times density, that is kilogram per meter cubed, times speed V, which is meters per second squared. Now remember, L was raised to power 2 and V is also raised to power 3. So when I simplify this, I'll first maintain the numerator, kilogram meters squared S power negative 3 denominator. I also have kilograms. Now I have M power 2, M power negative 3, and M power 3. So that gives me only M power 2. Then I have S power negative 1 raised to power 3, which will be S power negative 3. So you and me notice that these terms are cancelling out. Kilogram with kilogram, M power 2 with M power 2, M power negative 3 with M power negative 3. So I will conclude that C has no what? Has no units, because the terms have actually cancelled out. So C has no units. Okay, so I hope that is home and dry. That is very easy. Let's continue. We are almost done. Let's move to question number 29. Question number 29. Show that the SI units of energy per unit volume. It's now energy per unit volume. Kilogram per meter per second squared. Energy per unit volume. The base units of volume are meters cubed. The base units of energy are kilogram meter squared per second squared. So we now divide energy per unit volume. We have the units kilogram meter squared per second squared divided by meters cubed. When you divide, you subtract here the powers. M power 2 divided by M power 3 becomes M power negative 1. So this simplifies to kilogram meter squared per meter S power negative 2. That would be the SI units of energy per unit volume. Okay, question 29 was very easy. We have to move to question number 30. Question 30. Question 30. For a wire extended elastically, note or remember from the formation of solids, a material is extended elastically if, when the deforming load is removed, the material returns back to its original length. That's why when we say it is extended elastically. So the elastic energy per unit volume, X. I want you to note that X is energy per unit volume. And in the previous example, we have seen the units of energy per unit volume. C is a constant, epsilon is the strain, E is the Young modulus. Show that C has no units. Show that C has no units. Because we are to show that C has no units, let's begin by making C the subject. So C is going to be equal to X divided by epsilon squared times Young modulus. That is C. But remember, X was energy per unit volume. It was energy per unit volume. And in the previous example, we have already seen the units for energy per unit volume. So the base units here, so X is energy per unit volume, and the base units were kilogram per meter per second squared. Kilogram per meter per second squared. Those were the base units of energy per unit volume. And epsilon is strain. Strain has no units because it is extension over original length. So strain has no units. And then E is Young modulus. Young modulus is stress over strain, which is force times original length over cross-sectional area times extension. Area meters squared, force kilogram meter per second squared, which makes the base units of Young modulus to be kilogram per meter per second squared, because we have kilogram meters per second squared divided by meters squared. So we now substitute. The base units of C will be those of X, which are kilogram per meter per second squared divided by those of E, because epsilon has no units, so it will not bother us. So this will be over kilogram per meter per second squared. So we cancel out term by term, term by term, term by term. Since all the terms have cancelled, we conclude that C has no what? C has no units. As simple as that. Okay. Question 30. Question 30. Is it question 30? I guess so. Oh, we are from question now. Question 30. It is 31. Okay, question 31. Two wires, each of length L. So L is length, are placed parallel to each other a distance x. So x is distance, as shown. I think we will see this expression in electromagnetism or electromagnetic induction. Each wire carries a current I, so I is current. The current gives rise to a force F. F is a force, where K is a constant. So K is a constant. Then I think the question continues to the next page. So K is a constant. Time the SI base of K. Time the SI base of K. So just write here the expression that we have been given. We have been given that the force F is equal to a constant K times I squared times L divided by X. Then L has been defined as length, so the bases of L are meters. X has been defined as distance, so the bases of X are still meters. Then I has been defined as current, so the bases of I are going to be amperes. F has been defined as force, so the basis of force, mass times acceleration, that will be kilogram meters per second squared. So now what remains is very easy. We want to find the basis of K, we make K the subject, so K is going to be F times X divided by I squared times L. So the basis of K will be kilogram meters per second squared times X, which is meters, divided by ampere but squared times L, which is meters. So meters has cancelled. This one can cancel with that one, so you remain with kilogram meters per second squared per ampere squared. Those will be the bases of K. Okay, that is fine. Next is question number 32. Question number 32. Question number 32. The unit of resistivity expressed in terms of base units is given by that. Which base units are X, Y, and Z? Huh. Well, to avoid recalling the base units, since we already have the basics, we can still rederive the units of resistivity and verify. We said from resistance is equal to rho L over cross-sectional area. Then we know the base units of area as meters squared, length base units as meters, and we knew that we could find resistance, the basis of resistance from power is equal to I squared times R. So R is equal to power over I squared, power being kilogram meters squared per second cube, and I being ampere squared. So the basis of R were actually kilogram meters squared per second cubed divided by ampere squared, which becomes kilogram meters squared per second cubed per ampere squared as the basis of resistance. And we saw that the basis of resistivity was R times cross-sectional area divided by L. So the basis of resistivity were actually kilogram meters squared per second cubed per ampere squared times area, which is meters squared, divided by L, which is meters. And this simplifies to kilogram meters squared times meters squared divided by meters, it becomes meters cubed. Then S becomes S power negative 3 and A is A power negative 2. So X is most likely meters because X is cubed. So X, that is meters, and then Y, that is amperes, and then Z, that is seconds. So we have answered that question very smartly. Okay, so question 33. Question 33. Question 33. So the elastic potential energy E. So E is energy. Elastic potential energy is given by this expression here. Rho is density, G is acceleration of free fall, A is cross-sectional area, and C is a constant. Okay, the question continues. The question is continuing. Next slide. Determine the SI base units of C. SI base units of C. Maybe just write here the expression that we need. Energy has been given as C times rho squared times G squared times cross-sectional area times L naught cubed on the previous slide. C is a constant and it's the quantity whose units we need. So making C the subject, C will be equal to energy divided by density squared G squared area L naught cubed. So, okay, so rho is density. Base units of density will be kilogram per meters cubed. Okay. G is cross-sectional area. Base units of G will be meters per second squared. G is acceleration of free fall. A is cross-sectional area, that will be meters squared. And L naught was given as the original length. L naught will also be meters. Okay, I think I've stated all the units. E is elastic potential energy. Energy as units as kilogram meter squared per second squared. We have already established that. So now let's find the base units of C. Base units of C. So C is going to have base units as, I don't want to put equal signs on base units. So I will have to rub off the equal signs. Don't want equal signs. So C will have base units as E, which is kilogram meter squared per second squared divided by kilogram per meters cubed times, okay, this is squared by the way, times G, meters per second squared, but is also squared, times meters squared times m power 3, because it is raised power 3. Let's first of all simplify the numerator maybe. So this is kilogram m squared s power negative 2 divided by, in the denominator you have kilogram but it is squared. M power negative 3 raised power 2 becomes m power negative 6. M power 2, that becomes plus 2. M power 2, that becomes also plus 2. Then let's see S. By the way, this is squared, because it is kilogram meters power negative 3, the whole of it is squared. So that should be squared. So we have S power negative 2, again raised power 2, it becomes S power negative 4. We multiply the powers. So when we simplify, haven't I forgotten one m? M power negative 3 raised power 2, that's negative 6. That's 2. That's 2. There is another m power 3 here, which makes this plus 2 plus 3. Let me just rub that so that I rewrite it very well. So this is kilogram power 2 multiplied by m power negative 6 plus 2 plus 2 plus 3 times s power negative 4. So this becomes kilogram m squared s power negative 2 divided by kilogram squared. This will be m power negative 6 plus 7. That is negative 1. Sorry, positive 1. That is m power 1 actually. Then times s power negative 4. So we are now simplifying. The base units would be kilogram divided by kilogram squared, that becomes per kilogram. And m power 2 divided by m power 1, it becomes m. S power negative 2 divided by S power negative 4, I think it becomes S power 2. Mathematical window, I will say S power negative 2 divided by S power negative 4 becomes minus negative 4. We subtract the powers, which becomes S power 2. So this will be actually the unit, the base units of C. All you need to be careful with is the algebra. There's nothing much here. There's nothing complicated here. Okay, next, we are almost getting done. Question number 34. Question number 34. Okay, the volume V, so V is volume of a liquid that flows through a pipe in time t, so t is time, is given by that equation. P is pressure, difference between the ends of the pipe, radius r, length l. The constant C depends on the frictional effects of the liquid. Determine the base units of C. So straight away I'll make C the subject. C will be equal to volume per unit time multiplied by 8 times L. Divide by, is that true? I'm making C the subject? No, that's not true. So C is going to be pi P R power 4 divided by 8L times V over T. I've made C the subject. Listing the units: R radius, base units meters; L length, base units meters; and then P is pressure, P is pressure, P is pressure, P is pressure. Let me write here then. P is pressure, base units are pressure is force over area, so that is kilogram per meter per second squared, force over area. And then V over T, I will take it as one quantity, volume, that is meters cubed per unit time, meters cubed per second. So we now substitute. Pi and 8 will not affect the base units. Therefore, we shall say that the base units of C will be equal to those of pi, kilogram per meter per second squared, that is for P, times m power 4, radius is raised to power 4, divided by L is meters, V over T is meters cubed per second. Let's simplify. Simplifying, I see m power 4 in the denominator and m power 4, that one cancels. Or if you can't see that, you can check, this becomes kilogram. M power negative 1 times m power 4, we add the powers, divide by m power 4 in the denominator, we remain with m power negative 1. Then s power negative 2 divided by s power negative 1. Remember, we subtract the powers. S power negative 2 minus negative 1, it becomes s power negative 1. So those will be the base units of C. I hope that is home and dry. Next. Next is question number 35. It's almost the last. It's almost the last. State the SI base units of F, rho, and V. R is radius, V is speed. So V is going to be meters per second. Rho is density, density is kilogram per meters cubed, kilogram per meters cubed. F is force, force is mass times acceleration, so that is kilogram meters per second squared. I think that one is home and dry, that is easy. Next part. That is the continuation of that question. Question 35 is continued. Use base units to determine the value of k. So the expression we have had in the previous slide is that f is equal to b r squared times rho times v power k. We want k. So here, because k is a power, we are going to use homogeneity. We're going to equate base units on both sides of the equation. So F was force, that was kilogram meters per second squared, equals to B is a constant and K is also a constant. Both don't have units, so B will not affect the units. R was radius, so this is meters squared. Rho was density, which is kilogram per meters cubed. And V was speed, which is meters per second, but this is raised to power K. So I need K. I just need anything which is raised to power K to help me find K. This side I have M power 1. This side I have M power 1. The other side I have M power 2 plus negative 3 plus K. Equating the powers, I have that 1 is equal to negative 1 plus K, which makes K to be equal to 2. I could also have used the S. On the left, I have S power negative 2. On the right, I have S power negative 1 raised to power K. It becomes negative K, which makes K to be equal to 2. So either way, K is still 2. Okay, next. Next is, I think, the last question. The last question, lastly, is question number 36. Question number 36, and perhaps the last question. The density rho of a rock from which the pebble in B is composed is given by that. So rho is density, n is an integer, m was mass. I don't think this question is complete, but I know m is mass. M is mass. R is radius. L is probably length. And the question is, we want to find n. N being a power, we shall use still homogeneity to find n. On the left, we have base units of density, which are kilogram. Base units of density, which are kilogram. I don't know what is happening to the pen. So the base units of density, which are kilogram per meter cubed, should be equal to mass. Mass is kilogram. Radius, that is meters power n, divided by k. K is a constant with no units. So L is a length, which is going to be meters. So I can simplify. On the left, I still have kilogram per meter cubed. On the right, I have kilogram m power n minus 1. So I can equate m, sorry. So I have m power negative 3 being equal to m power n minus 1. So when I equate the powers, negative 3 is equal to n minus 1. So n becomes negative 2 when I equate the powers. And if n becomes negative 2, this expression could precisely be written as either rho equals to m r power negative 2 over kl, or for further questions, it would be m divided by kl r squared. So that will be the more precise expression, because next you may want to use it for finding the uncertainties. I know it has been a long lesson, but then I had to do as many examples as possible to make you more confident. I think we have come to the end of this lesson, and if you have been resilient enough, note that this is the end of base units. If you have been resilient enough, you must have now developed confidence in manipulating or deriving base units of quantities. Thank you for watching. I hope if you have any question, you can leave it in the comment section. Like this video, share with friends studying AS Physics 9702, Paper 1 and Paper 2. Thank you for watching. God bless you. Stay nice. Bye bye.